Okay, the question I posed at the end of the last video was, how do we rewrite this? How do we reconstruct this? And what is the probability if we redefine our target as tails, as failures, right? I want to know what's the probability of 7 tails. I could have written failures, but I'm going to write tails this time. I'll show you why in a second. I think you'll see why. Well, I know that if I'm talking about 7 tails, whether it's termed a failure or a success, that becomes my target event. And I'm still working with the same coin. So what I'm going to do is I'm going to say to myself, let me set it up, 10, choose 7 of the event that I'm seeking. So I'm not calling it a failure anymore because I want to avoid confusion. Anyway, it's tails. Times the probability of that event that I'm seeking times the probability of its complement for the remainder, 10 minus 7, which is 3. If you work this out, you're going to find that it is exactly the same probability. And logically, it should be, because if we're working out the probability that we would get 3 heads, that's leaving unspoken that we'd be getting 7 tails. But it's obligated, we are obligated to see that that would be true. Specifying 3 heads in a series of 10 flips is specifying 7 tails. It's just different ways of describing the same event. So this has to come out the same. It's obligated to come out the same, and indeed it does. Okay, let us clear some room. I'm going to clear all of this. And I want you to understand, at some point, I think it should be said, the basic presumptions, the basic assumptions that must be true for binomial probability. As I get used to this YouTube thing, I'm beginning to utilize editing more and more. I'm getting pretty sophisticated. I'm stopping the camera and restarting it in the middle of videos now. So I consider that a pretty strong move upward. Anyway, so here are 4 things I want you to remember about binomial probability. First off, there's a fixed number of trials. We know that implicitly. Every binomial probability question I've been talking about, or you'll be asked either in a test or in a textbook or whatever, is going to talk about a situation like, given that we have this many coin flips or this many rolls of a dice, what's the probability that such and such a thing would happen? Yeah, you can do binomial probability with the rolling of a dice. I know that there's 6 outcomes. I'm going to give you a dice problem at the end of this, actually. And you're going to have to use the binomial probability theorem to solve it. I think you'll be able to do that, though, at the time, even though it seems like you ought not to be able to. Each trial is binomial. That's the second rule. Well, duh, it's the binomial probability theorem that we're talking about. That means that every outcome will result in every trial will result in one of 2 outcomes, either success or failure, heads or tails, up or down, hot or cold, just like we talked about in part 1 of this video. This we need to recognize. Sometimes it's assumed, but we need to specify it and recognize it consciously. All the trials are independent. If they're not independent, we can no longer use the binomial probability theorem. And finally, the probability of success and failure go unchanged. It kind of seems like Rule 4 and Rule 3 are the same rule, but they're really not. Rule 3 tells us that each trial is independent. That means that the given outcome for one trial does not affect the trial following it, right? So you don't have a greater probability of a heads if you keep getting tails 20 times in a row. Sometimes people in Vegas or Atlantic City think that way, and it's not really true. So there's no influence from one trial to the next. It's also not the case, and I'm talking about rule number 4 now, it's also not the case that there's anything funny about the experiment itself that you're doing. The coin doesn't wear out, for example. If it starts out with a 2/3 probability of heads, it doesn't gradually mediate back to a half and half split in terms of the probabilities of heads and tails. It doesn't change. That's different from the presence or absence of independence. It says that the situation itself goes unchanged, quite apart from any changes that ought not to be happening as a result of the previous trial, which is what rule number 3 is talking about. Okay, so let's do some problems. Here's our problems, and I decided to write them out on camera. I want to know, with a fair die, what is the probability of 4 6s? I'll put that in quotes, even though I'm not sure that that's correct grammar. I'm going to take that out. 4 6s in 10 trials. 10 rolls. What's the probability of 4 6s? Can you figure out how to use the binomial probability theorem for that? Yes, we remember that the die has 6 sides, but I think you can figure that out. Okay, with a fair coin, here's the next one. With a fair coin, what is the probability that x should equal 3 in, let's make it 6 flips? That's with a fair coin. Tell me what that probability will be, that you will get 3 successes in 6 flips. It's a fair coin, so you tell me what a success would be. Would it be heads or tails? I guess it's arbitrary. You can decide that. With our unfair coin, okay, same one. Probability of heads is 2/3. Probability of tails is 1/3. With that unfair coin, what is the probability of at least 2 trials, at least 2 successes in 7 flips? Go ahead and work that out. We're going to follow that up in another video in a day or two. I want to give you time to work on that, okay? Thanks a lot. Oh, and don't forget to like and subscribe.